Welcome back. I want to welcome Hayden. He's going to tell us about link homologies and knotted surfaces. And this is his first talk.
Thank you, Akram. Thank you in general to the organizers for the invitation for putting together a nice school and conference. So get the sort of housekeeping stuff out of the way first. As Akram said, it's going to be a mini course on link homologies and knotted surfaces. Our TA is going to be Ikai Tang. I don't know if you could give a wave. There you go. Great wave. All right. This is mostly going to be a board lecture, but I'm going to have a little detour into slides for some detailed stuff that's not as central to the main thrust of the lecture. But the slides themselves are on my webpage, and there's also a link to exercises on that page. So if you go to the bottom of the page, I don't have like a cute URL, so I do what I assume everyone always does for anybody. Kyle Hayden math. Yeah, there's also some Kyle Haydens are course keepers, photographers, etc. If you want to complain to them, I'm gonna be able to get a better domain name. But until then, Google it. Okay. So first question for you guys is, can you hear me okay, especially people in the back? Okay, great. And is this writing legible? Awesome. Okay, then let's really go for it. So what I want to talk about this week is link homology theories, which typically think of as assigning invariance to knots and links. Especially in the three sphere will be our focus, but we can consider it more generally for some of these theories in other spaces. And what we'll focus on will be knot floor homology and Kavanagh homology, and in general, these are sort of umbrella terms. There's lots of different flavors of this. So instead, what we're going to do is today sort of play dumb that we don't have any theory in particular in mind, and just try to talk about the sort of shared formal properties. We'll do a bit of a detour and get specific over here on the slides, but for now, we'll sort of be agnostic at the moment. So we're going to focus on knot floor homology and Kavanagh homology. We'll sketch the definitions of those extreme, or at least describe what the generators are, so we have a picture of what the objects are. But what do we want in such a theory? Well, we want it to take a link, potentially an oriented link, so not for a link L, S3, and we want to assign to that H of L, which for your favorite choice of your coefficient rings from commutative ring, this will be for us some bigraded R module. But my favorite ring is F2, and so or Z-mod 2, and so I'm just going to think of these as vector spaces often. But we want to keep in the back of your mind that we can have more structure, and that structure might tell us something topologically. It's not just fancy for fancy's sake. And we'll talk about what the gradings are, but we want to think about, in general, these as having two gradings. Let's say some integral gradings. And one of them will sort of essentially be a homological grading, and one of them will we'll think about it as some more geometric or some more specific information. Okay, but these will be sums over Ij, L. Okay. So this is sort of the prototypical setup we'll want. And it's not unreasonable to make a few demands of this, such a theory. So if the theory that you have in mind assigns an invariant to the empty link, then that should be our coefficient ring. And so this is where I begin to admit that I'm going to be intentionally hand wavy. So I said that we're really using quantum homology and not floor homology as umbrella terms, because there's lots of different variants of these tools. I'll make my best effort to, if not otherwise specified, whenever I'm writing a claim down about one of these theories, I'll mean it to basically be the most vanilla version, regular unreduced quantum homology, or HFK hat. And so, at least in particular for those specific flavors, we're gonna have the empty link assigned to just the coefficient ring. That's sort of a useful property to have. So I'll write, this is typically. What else? Well, we're saying that these are link invariants. So the sort of weakest claim we might make about that is that L up to isotopy, how am I writing this here? Gives us invariant H of L up to isomorphism. So a priori, even if our process for constructing the theory gives us a concrete object, some concrete, R module or vector space, however we're thinking about it, when we want to start using it as an invariant, we have to keep in mind that a priori it might only just be that the isotopy type of L determines the isomorphism type of this object. But in practice, we have sort of naturality properties, such that given more data, which might take the form of a fixed diagram, or perhaps base points, etc. We not only get some abstract isomorphism type, but we get that isotopies induce specific isomorphisms, well-defined isomorphisms. Or say isotopies can induce isomorphisms. And so that's a stronger type of functoriality. And it gives us the sort of first hint at what we really want to be using these objects for, or these theories for, which is, well, if I have an isotopy of a Naudera link, and I'm saying that that's giving you some explicit identification, some isomorphism between the beginning and the object assigned to the beginning and the end. Well, I can think of that as sweeping out some annulus, some embedded annulus in S3 across the interval. And that's, we sort of perhaps call that a concordance. And we're interested in these theories assigning homomorphisms to link cobordisms more broadly. Okay, so what do I want to say here? Okay, so a couple of just a quick moral thought. Here we just said that we get something assigned to this is going to be a rather contentless little picture, but okay, so maybe we get something assigned to trace of isotopy. And so we might wonder, more broadly, what if I have some link cobordism? Okay. Okay, but we're getting ahead of ourselves. Not quite ready to think about knotted surfaces and cobordisms yet. I want to pause for two reasons. One, to say, I forgot to say at the top, please don't hesitate to pause me for questions, comments, etc. And so let me first just pause and ask if there's any questions about this sort of general setup we're describing.
I have a question about the fixed diagram business. As I'm reading, it doesn't really make sense to me, because it sounds like if you're fixing a diagram, you're like not performing any Reidemeister moves at all, so no isotopies whatsoever.
Yeah, thank you. That's so, what I should say is, fixing a diagram, giving us a more concrete identification here. And then if we have, depending on the theory, what is needed, in particular, if I'm imagining quantum homology, I'm gonna want a sequence of fixed diagrams going between them. Thank you. Yeah, so that's a really key point. So we're gonna have to think about not just point A and point B, but all the intermediate points, and think about how we sort of progressively identify each step with the next, and what exactly these diagrams should be related by.
And so you're like parameterizing an isotopy with the fixed diagrams, and there's a way to do that with base points as well.
So depending on the context, right, so in particular, base points will matter, or for our context will matter for not floor homology. And there, what we'll have to think about is, I mean, here I'm drawing on cobordism, but you know, we want to think about some, for example, some way of interpolating between base points using a graph on the cobordism. Actually, we're not gonna use the graph version of DCOP, but we'll use something that sort of addresses the same basic question of being, for whatever extent the decoration fits into our construction, we'll need a corresponding way to fit that much data into whatever our next dimensional, in our case, two-dimensional objects are that interpolate between them. Sure. Okay. Yeah, thanks. Great question. Yeah, any other questions before we take a quick impressionistic look at the two main players?
I have a simple question.
Please.
Is that IJ like both elements of Z2 or that a pair in Z2? Like
Yeah, so I'm thinking about this as a pair of integers. Yeah, thanks. Great, yes, so ordered pair of integers. Yeah, great. Any other questions? Okay. So what I want to do now is second reason I'm pausing, now I remember. So we'll be able to say things more concretely fairly soon, but in general, especially for the lectures 2 and 3 this week, we're going to focus a lot on quantum homology. I have to say the overall strategy will be today to focus on what these two theories have in common. Lectures 2 and 3 will focus mostly on quantum homology. That's mainly because we'll be trying to talk about some things which you can imagine doing in either theory, but we need less background to actually work explicitly with quantum homology. We will be able to do more hands-on things. And then we'll keep in our mind, you know, what analogous tools we have in not floor homology. And then on the fourth lecture, that will be just about not floor homology. Okay. So that said, I'm going to, depending on your perspective, either tease you or torture you with a very brief sketch of what these theories are. There will be a bit more detail on the slides that are on my site in case anyone wants to look them up after. But what I do want you to remember here is that I'm just trying to sort of like establish a sense of what these objects are, and in particular, give you some way to think about what are the concrete elements that generate these theories. Okay, so with that declaration made, just to check on the tech side, I should share my, I should share my screen now, and that'll be good. Lost a visual on the organizers. Oh, there's, okay. Okay. All right, so I should have set up my clicker with this, but okay. Sorry for the pause. Okay, so the first thing I want to do is just describe at a very overview level what's going on in not floor homology. So let's start in the top left and don't look beyond that yet. Informally, let's say we start out with some knot. We're going to want, for the sake of our construction, to put two base points on it. Among other things, we can think about this as if we have a ordering our base points, this would give us well, let me not go into this. I'm gonna attempt to keep myself from blabbering. Start with a knot, we're gonna pick 2 points on it, and we're gonna associate to it some Hager diagram for the 3-sphere. And in the first construction here, this is gonna be some genus 4 Hager diagram, so that's gonna be basically a decomposition of S3 into 2 genus 4 handle bodies, meaning along this standardly embedded, in this case. Sorry, but yeah, standardly embedded. Genus 4 surface, and we have 2 sets of curves which bound disks on one side or the other, in one handle body versus the other. And you know, the algorithm which produces, in this case, such a diagram is going to come from sort of taking the sort of first singular projection of the knot, and then the choice of curves is going to give us data for crossing information. But one way or another, what is this diagram doing? It's giving us some Hager diagram for S3, where in this case, one of the curves, the one at the very top, the red alpha 1 curve, that's going to be effectively a meridian for our knot. And if we got rid of it, we would essentially be giving ourselves a decomposition of the knot exterior. Okay. But more generally, you don't have to have that the construction of such a Hager diagram adapted to your knot. On the right, we have a much simpler looking one. And the point there is that somehow, in particular, if you try to go from Z to W and back, where you're only allowed to, in this case, so we got right cross over, we're not gonna be able to say it right, over blue versus under red or vice versa, or whatever, you're gonna trace out the knot. Okay, but the point is that such data is what we need to set up our theory. And roughly speaking, what are the generators of the theory gonna be? Well, they're gonna be G tuples of intersection points where such a point xi lies in alpha I intersects some beta j, so some red curve intersects some blue curve. J here really needs to be the image of I under some permutation of the symbols. So basically, you got like a Sudoku thing going on. You got one intersection point per curve, okay, and that's going to sort of then be distributed across pairings between the alpha curves and the beta curves. Okay, and that's how we might think about this diagrammatically or combinatorially, but sort of in the geometry that really factors into the definition, we're secretly thinking about this other ambient space, symmetric product of F, G copies where G is the genus. So here we're taking F mod the action of the symmetric group. And the point is that because all the alpha curves are pairwise disjoint, their product naturally embeds into this space. Same thing with the beta curves, and we get 2 G-dimensional tori, alpha 1 through alpha times alpha G, beta 1 through beta G. And now we're going to look at intersection points between those. And that sort of, if you trace through, is exactly giving the sort of diagrammatic condition on intersection points, G couples of intersection. Okay, so very briefly stated, but before we say anything about the differential, are there any questions about what I'm actually describing as the generators of this thing? And again, it doesn't matter too much because we're actually not really going to be explicitly working with it. I just want you to have a sense. Yeah, please.
Are both of those possible diagrams up top? Like, can you make either of those for any length or?
Yeah, what's the right way to put this? There's for a given class of links, there are different diagrams or classes of diagrams that are naturally associated to that presentation of them. The first thing is in some ways the most like simple-minded, like we can always associate clearly some diagram. Depending on if you have like a bridge presentation or different things, not to make it more or less different. But in particular, one thing that you cannot always enforce is having low GMs. So it's, it has to do with the fact that the trefoil is particularly simple, that it can even have a genus 1. There's a genus 1 diagram for S3 adapted to the, yeah, that's a good question. Okay, yeah, other questions? Okay, so just a brief word on the differential, very briefest of words. So here, the boundary map is going to be defined analytically. We're going to basically count quote unquote homomorphic disks that map into this metric product with some boundary condition. So depending on if we think about these as homomorphic strips or homomorphic disks, the point is that we have some subsets, in this case, the points -1 and 1, that should sort of be limiting to our points, our intersection points. And the halves of the disks that we separate have to be mapping embedded into the alpha tori versus the beta tori, 1/2 on each. And so there's some way to say that this is going to give me a contribution towards a boundary map between x and y, and not going to say more than the fact that constructing such a well-defined count is and computing it is sort of an analytic endeavor. Generally speaking. Okay, but what do we care about? For one thing, we said there should be some gradings floating around. Here we have our two gradings, the Maslov grading M, which we'll think about as sort of playing the role of a homological grading. It's the thing which is shifted by the boundary map. And then the A grading, the Alexander grading, and that's going to be preserved by the Alexander, by the differential. So we'll see that our right off the bat, we're going to see that this is now decomposed. The result homology theory is going to decompose as a direct sum of H of K subspaces M comma A, where M is our, again, our Maslov grading and A is our Alexander grading. So this is some homology theory, and if you take its graded Euler characteristic, that is, some alternating sum of dimensions with attached to some formal variable, what will you get? You'll get exactly the Alexander polynomial. So this categorifies the Alexander polynomial. Okay, so the moral takeaway here is this theory is sort of intrinsically geometric, and actually defining it, computing it requires sort of analytic considerations. So again, taking this with a grain of salt, any questions before we, in the slightly more detail, sketch what's going on the Kavanagh side? So, question?
Sorry, like, I don't understand what what's it called, the boundary map is doing.
So I'm definitely not stating what it is.
Oh, okay.
Yeah, sorry, so that's clear. I'm trying to give you a sense of what's going into the boundary map, but certainly not defining it.
Okay,
Yeah,
great.
thank you. That's an important point. We'll get a bit closer to defining the actual map on homology, but here I'm just indicating that if we're thinking about the differential of some generator X, the point is that the generators that will show up as coefficients in the boundary of X will somehow be generators that are on the other end of some holomorphic disk from it, suitably oriented. Yeah, thank you. Okay, great. So let's give quantum homology the same treatment. So here, we're working sort of more fundamentally diagrammatically and combinatorially. So the first thing is, pick your favorite diagram and technically enumerate the crossings. And once again, I'm going through this fast, but the point is that the details are just to give you sort of a vibe, not to have you track all the details. And if you want, these slides are on my site. Okay, so that's step one. Step two is to construct what we'll call a cube of resolutions. So for every crossing, there's sort of a choice of two ways to smooth it. And we want to consider all the possible total smoothings associated to the n crossing. So it'll be 2 to the n possible ways to smooth this. And we sort of already see that there's some natural coordinates on here, given by just a lengthened sequence of zeros and ones. Starting on the left, we applied just the 0 resolution to all crossings. Going up and to the right, we have 2 0 resolutions and 1 1 resolution. And you can keep going, and eventually all the way on the right, we have just 1 resolutions. So we can take this, and what do? Well, we're going to take those little squiggles and assign them some labels. Those labels will be in this object A, which is our joint X, where R is whatever our coefficient ring was. I'm gonna often just think about Z mod 2, so things are really simple. But a join some variable, and then we're gonna kill the square of it. So really, we're just looking at labels 1 and X in that case. But yeah, so this is all possible choices of labeling. And so each one of these little pictures, like here's 4 generators, there's 6 generators, etc. They're sort of loosely stuck on top of where they sat in that cube of resolutions. But the takeaway so far right now is that this is still fundamentally diagrammatic. And if these are the, actually, do I have more to say here? Yeah, okay. So I'm not going to define, I'm going to very quickly jump over the next slide. If you want to look at the slides themselves, they'll define what these gradings are. But the point is, just like we had 2 gradings in the non-floor setting, here we're going to have 2 gradings. One, which is going to be a homological grading, and that's going to be independent of the labeling. That's going to be determined by the initial diagram and the smoothing. And then the quantum grading is going to care about the particular choice of labels. Okay, so I'm going to very briefly jump over this. Maybe I'll just say a couple words, but we can again see we have to choose, count the number of positive, number of negative crossings. The homological grading is going to be essentially the number of 1 resolutions minus the number of negative crossings in the diagram. So that has nothing to do with the labels. And the quantum grading is going to now involve labels. So it's going to be the difference between the number of 1 labels and X labels. And then just some sort of fixed term space in the smoothing. So the homological grading of the smoothing, and then plus the right the diagram. Okay. But again, I'm not intending you to gather the details about homological quantum grading, but just again emphasizing that they're somehow geometric and diagrammatic. And again, if you want to look at this afterwards, you can see an example. The reason I'm including this is because there's been an exercise for anyone who wants to practice calculating it. Again, continuing our sort of vibed tour of these 2 theories, we somehow turn this into a chain complex. The point will be that our maps sort of go along increasing edges in our cube. So they're going to change 0 resolutions to 1 resolutions. And then we're going to need some way to sort of say what happens to the smoothing data. Okay, so I'm going to jump over that. Am I? Let's see. Stuck on this. Okay. So again, if you want to look at the slides later, there's, tomorrow's lecture will actually start with this, but again, for anyone who wants a sneak preview, there's some data on the label rules. Okay. But again, the key point is that these are sort of fundamentally combinatorial. And so here, for example, actually, let me go back for 1 second. If all you knew nothing about the gradings, then if you try to compute this homology, you could, and you would just get something which was sort of abstractly isomorphic to, if we're working with Z mod 2, 6 copies of Z mod 2. If you actually were working with gradings, you'd find it distributed in the following way. So homological grading here is ranging from h equals 0 to h equals 3. It's not a coincidence here that there are no negative crossings and the minimal h grading is 0, and the number of positive crossings is 3, and the maximum h grading is 3. It's not a coincidence. And then we're seeing the sort of distribution, this sort of somewhat diagonally looking along this HQ plane. That's also not a coincidence, but only pointing it out sort of phenomenologically. Okay. And if you were to factor in gradings, sorry, not gradings, if you were to factor in signs and work over Z, then we would get something which is isomorphic to Z to the 4th plus a copy of Z mod 2. So it can contain torsion, for example.
Is Q always on?
Yes, so for the parity will depend on the number of components. The parity will be the same as the number of components, at least for the unreduced theory that for main theory we'll look at, and that's right, it'll always be either even or odd. Yeah, thanks. Great. Yeah, okay, so this this was our very, very brief glimpse at what's going on with these theories. For the most of the rest of today, we're not going to say anything that involves the specifics of the constructions. But before we move away from the projector, I do want to point out that even though we really want to be thinking about surfaces, there's a lot to be gleaned if you do want to think about surfaces by just first thinking about these objects. And in that direction, I want to point out that there's really lovely software for calculating such things. So let's start with not job. So the exercises include a, let's see the way to do this. Okay, so this is programmed by Dirk Schutz. There's an install link in the exercises. And for example, maybe I'll put in my favorite, actually to make it more random, and put in a braid. Hello, braid. And let's go A, B, oops. Oh, just some random one. To show you the diagram. Oh, cute, it's figure eight. And it can calculate, for example, just plain old quantum homology, integral coefficients. And yeah, so here we can see some other features that we saw before. This is symmetric. The gradings, it's related to the fact that the grade knot is hyperchiral, etc. So there's really lovely software for doing things like this. You can change your coefficients, work, for example, mod 2. Okay. And then on the not floor side, if you install Snappy, which again, there's an install link to, then that's the smallest font I've ever seen. That's not the zoom I meant. I think this is gonna tell me I have to restart the program. We'll see. Oh, lovely. Okay. Yeah, of course. All right. So let's say I do 4.1, and I can do K not floor homology. And it's going to give me a bunch of not floor theoretic data. But in particular, it's going to tell me what the ranks are in the bigrading. So you can reconstruct the same type of data we were looking at before. This is saying that in Mazalov-Alexander grading -1, -1, it's rank 1. By grading 0, 0, it's rank 3. And by grading 1, 1, it's 1. I should say this is over Z-mod 2. I think that this program can do like something like any coefficients in Z-mod P for any, maybe it's prime P less than like 200 or something like this. But I think the default is Z-mod 2. Okay. So the last thing I want to point out is that if you want to go really crazy, what's really fun is to combine this with something like the Kirby calculator. And these programs can talk to each other quite nicely. So maybe I'll draw roughly the great knot, make it look pretty. You can do, for example, export diagram snapG. Oops, those are not this. And it's pretty easy to import things. I'm not intending you to follow this, but just trying to give you a sense of how simple the workflow is. Okay. And I could send, oops. Send a snapB, and I should get the same thing. If I do j.link.not or homology. Okay. Oh yeah, there we go. Okay. All right. So anyway, just some fun things you can do. There's some suggestions in the exercises for stuff in this direction. All right. Any questions about this quick sketch of the material, the sort of underlying theories, this impressionistic take on them before the projector goes away? That's not like a punishment, like if the projector goes away. Okay. So then let's go ahead and put that away and go back to being analog. Okay, do I need to do anything else here? On the text, I mean, I'm good now on the text side of it. It's just top screen share. Okay, so let me go ahead now and put the projector away. seconds. So why am I blabbering on and on about these objects? We're supposed to be talking about knotted surfaces. Oh, you know what? Well, before I can do that, I meant to mention, I said that knot-floor homology categorifies the Alexander polynomial. So, you know, sort of, on the other hand, component homology, you do the same construction, will spit out the Jones polynomial. So you're sort of again seeing on the floor side something sort of fundamentally geometric. The Alexander polynomial has lots of sort of natural geometric properties we can extract from it and use to study it. On the other hand, homology, but Jones polynomial sort of is somehow more combinatorial and connected to, for example, representation theory and things like this, a little less directly geometric than Alexander polynomial or floor homology. Okay. So question I should have asked the organizers at the start, but we're running 50 minutes, 55 minutes. Okay, great. So now let's get to the main event. So the wonderful thing about the types of objects we want to study is that if we're given a link cobordism sigma between links L and L1, so here sigma is in S3 cross 0 to 1, and we have L naught at one end and L1 at the other. Then we'll get a homomorphism H of sigma, which will be, let's see, how much detail do I want to say about this? So this will go from H of L naught to H of L1, and this will be some graded R module homomorphism. Okay. So we said before that sort of isotopies should induce isomorphisms. Here we're saying that arbitrary cobordism will induce just at least some homomorphism. So what goes into this? Well, the general idea turn it on. Okay, so the general idea is to say, well, I have this sitting inside of S cross 0 to 1. So as a first step, I'm going to perturb sigma such that the restriction, let's say just like, such that sigma into S3 across 0 to 1, and then the projection to 0 to 1 is Morse. And technically, we'll probably also want to assume that any two critical points have distinct critical values. So at trip points have distinct values. Then the point is that, so perhaps, you know, based on Mark's course, we know where this is going. That's going to exhibit sigma as a movie of links LT, which is just the sort of, if I give this composition a name, what's the whole thing? I guess, P. So all but finitely many of these are going to be smooth links, and of these links related by elementary coordisms and isotopy. So, by the way, are these switchable? Like, does this go all the way up?
No.
No, okay. Oh, I see. Yeah, there we go. You're strong enough. It's switchable. Yeah, okay, gotcha. I was just wondering if I could make it easier for people to see down here. So, okay, so let me just point out, this is gonna be elementary, births, saddles, and death.
You can also lower the dot cap.
Lower the.
That doesn't move.
That doesn't move.
Oh, sad.
Okay, so if anything's not legible, I'm happy to read it. Is there anything in particular if you read aloud? Okay. So, so what we'll need is to say, okay, well, I know how for each intermediate link to assign the this object H of L.
No?
Yeah.
There's no light on for here.
So someone,
Yeah, cool. So we know how to assign H of L to each one of these. And so the point is that we get the compositions. H of L0, H of, I'll call it LT1. H of L DN, H of L1. Okay, where all of these are elementary. So what we need to do with these stages, we need to assign to the sort of standard elementary coordisms. Okay. So you need some way to say, if I add, for example, a disjoint unknot, when I cross a minimum, what does that do? If I have a across a saddle that merges two strands or splits the strand into two, what do those do? Okay. So we'll describe examples of what those look like tomorrow. But again, we're sort of here agnostic about which theory we're talking about. Okay. So sort of out loud, let me say this. So we'll talk a bit about invariance tomorrow for quantum homology, but the point is that just like the underlying theories, the definitions of these maps are going to sort of reflect the nature, either defined sort of analytically in the floor setting, defined sort of combinatorially in the Kovanov setting, and then the proofs of invariance reflect these flavors. So for invariance of these maps, well, I should say, change this. These maps, H of sigma, are invariants of sigma up to isotopy rel boundary. So the proofs of those, for example, the proof for the Kovanov homology maps, that's going to involve, for example, the keywords Carter Sato movie moves. for example, if I have locally just a product cobordism near some region of some surface, well, that should be giving me the same map as if I instead, wiggle my cobordism so that in the projection, I temporarily see an R2 and then it's undone. The point is that topologically, those are going to be isotopic surfaces, roll boundary. So those better induce the same map. So what you need to do is show that under the movie moves, the maps are well defined. Sort of corresponding buzzwords for the floor periodic setting. Is that we need to do sort of Morrison surf theory for S3 of 0 to 1 sigma. So we need to think about the different ways that, especially in terms of the relationship to handle diagrams, different ways that changing this, embedding and thinking about the changes in the Morse function will play into the theory. Okay. So briefly, if I could say a couple more things briefly before we wrap up, started a moment too late. Let me just list to close a few general formal properties that these will have. So the first thing is they satisfy a composition law. So if I have sigma as a union of sigma naught and sigma 1, and actually I'll say as a state it as a composition, then the map associated to sigma is the composition of the maps associated to its pieces. Right, so here I'm picturing L1, we'll call this L1/2, and L0. So I glue them together, I just get the composition of the associated maps. Again, typically, and in particular for the most simple setups, grading shift is determined by the topology. And so this is true just as stated in homology, but for not for homology, this is true if we use the simplest decorations. Okay, but then in quantum homology, this is going to map HQ to KH, H, Q plus the weather characteristic. L0, L1. Okay. And then I think do I have time to say this? I usually want to think there's an exercise about it. So closed surfaces, those might one of the most basic cases to be interested in. Here, we know that we are going to have a map from the invariant of the empty object to the empty object. So that's just from R to R. And so for quantum homology, so that this is a genus G surface, then in fact, it's independent, in both theories, these were independent of the embedding. Genus G, then KH of sigma is multiplication by 2 if G equals 1 and is 0 otherwise. So closed tori induce non-trivial maps, but everything else vanishes. For HF over Z mod 2, we get that the map is the identity if G is 0 and 0 otherwise. And so okay, so the last thing I'll say out loud is definitely burning my overtime. One thing you can immediately prove between combining this and this is that, for example, any slice disk is going to induce a non-trivial map, no matter which way you look at it. So if I take a slice disk and glue it to itself, reversed in time, I get some closed sphere. For example, in HF, that's going to induce the identity. And so if I split that thing down the middle, it better be inducing a non-trivial map. Can't play the exact same trick with quantum homology, but if we take that sphere and then just tube on a little handle to make it have genus 1, then it will have to induce multiplication by 2. So if you split that map open or along one of the disks, that has to be non-zero. Okay. Okay, so I'll stop sort of our discussion of the form properties here. Tomorrow we'll pick back up with a quick discussion of some applications before getting our hands dirty with quantum homology itself.
Do you mean the last pages of HF?
HFK, sorry.
Oh, okay.
Thank you, HFK. And I should say, for some reason, I wrote sort of in scare quotes on my notes over Z2. I think that's maybe just for naturality reasons. I should maybe revise my slides and see if it's sort of carefully checked for other coefficients, but this is defined in the same way or well defined. Yeah, so there you go.
Experience when links that sort of like regardless of the cohort, or is it all like dependent on like the cohort?
So you're saying, trying to understand, so you're saying, do the cobordism maps give rise to invariance of the links themselves where the resulting thing is independent of the construction of the cobordism, but it's somehow more than the invariance in the module that's assigned to, or the vector space, or the homology group of the knot. Yeah. So depending on how it thinks about it, the answer is yes, or at least maybe a cleaner way to state it is the existence of it fitting into this type of functorial setup, this sort of TQFT type setup, gives rise to a variance you can extract. So for example, a variant of what's the way to put this? A variant of this that we will take a peek at with an extra best way to say this. Okay, I'll just state it this way. So the Lie homology is the variants of the sort of Kovanov type setup, and there you'll be able to use to understand the effect of cobordisms in that theory in such a way that you get, for example, slice genus bounds for the original knots themselves. Yeah. So yeah. Other questions? Yeah.
Not fair, but so this, forgive me if this was already mentioned, but that tells you it doesn't say this is worthless for studying closed surfaces of isotopic rays. Is that, I mean, it's good, that's good as a benefit.
So
any version of it that doesn't anything about closed surfaces of isotopic?
yeah, okay, so just to repeat the question, that if the very reasonable takeaway from this is that these theories and ones sort of share their properties are not going to be directly useful for studying closed closed surfaces because they assign the invariant that's just purely determined by the sort of abstract diffeomorphism type of the surface, not the embedding. So the one way in which I've seen an attempt to directly get invariance of closed surfaces this way is then to take some analog of what you do in your homology with the four-dimensional coordinate maps, which is create sort of a mixed map where I'm going to take my closed object, cut it open halfway, and do something clever with the maps that I get from each end into that middle cross section. And so in particular, Lipschitz and Sarkar have constructed such a mixed invariant for non-orientable surfaces. But my understanding is that there are no examples yet where I believe there's no examples yet where it's known to be effective. I believe that's the case, but I'll double check that before tomorrow, just so I can be on my best behavior. Yeah. Yeah. Does that answer that? No other questions? Effective meaning. Thank you. Effective meaning can actually distinguish embeddings of surfaces of the same topological type. And in this case, I should say, I think in that situation, perhaps the one thing that does factor in is about the embedding is the normal Euler number. So for non-orientable surfaces, we'll sort of have a very coarse algebra of geometric data about the embedding, which I believe is accessible by the mixed invariant, but otherwise we don't have examples of really distinguishing knotted surfaces that we can't distinguish using the most basic algebraic topology.
It's chair, it's actually. Getting out of it the whole time. Oh my god. You should try it. Yeah, good. I don't know, okay, let me see if I can.